Hello, friends. Welcome to the ATC Double Cut. My name is Micah Woods, and in this episode, I'm going to talk about a paradox that we have in Turfgrass, a paradox that you may or may not be aware of, but I think it's important to be aware of this. And it's a 8-minute read. It is on the ATC website. It is a post that I give the title, A Turf and Soil Paradox. I'll put a direct link to that in the show notes. And it says that it's an 8-minute read here. I am going to talk about it for a few more than 8 minutes. But in short, if we just do the 30-second version, what this paradox is that when you test the soil, the nutrient levels are often lower under the good turf, and the nutrient levels are higher under the poor quality turf. And that's a bit of a paradox because most people would expect that the soils with more nutrients would support higher quality turf grass, and the soils with lower nutrient content may have lower quality turf grass. Let me see, when I listen back on this, I'll see if I've gotten all those lower and higher matches all correct. Anyway, in this episode, I will talk about this. I will explain a couple of data collection projects I did that demonstrate this. And at the very end, I will say what the implications are, because if you're expecting the turf that's not as good in quality to have lower nutrients and somehow having that turf become better by adding more nutrients, and if you expect the good quality turf to be growing in soil with more nutrients, sometimes that may be the case, but in other times, as I will explain here, that is not the case. And then the question arises what to do about it. So I will explain how I consider handling that. And it's a very interesting topic. So here's what happened. This is a bit of a story that happened in the autumn of 2022. And in this blog post, I started off with this example. I said, one of ATC's soil testing clients wrote a couple years ago with this inquiry. And specifically, the inquiry came in October of 2022. And this client said, he sent a photo of one of the putting greens. He said, "You have any idea what this could be? Seems like it is getting worse. Any kind of deficiency maybe? Could it be like a spot deficiency in phosphorus? I have always thought it just got dry, but..." And then I showed a photo. And in the photo, at left, you can watch the video to see this if you're listening, or check out the blog post to see it. The original image shows a putting green with some green grass and some grass that's looks like it's gotten dry, or looks like it's some high spots that it's a little bit off color. It's not an even green across the surface. And then on the right side of the frame, I took that same picture and I ran an equalize filter through in my photo processing software, and that equalize filter will bring out things like off types. It often will bring out off types on a green. It will bring out the dry spots a little bit more. It'll bring out the stressed areas and make them a little bit more visible. And in this case, it just highlights some of those areas that my correspondent, my soil testing client, was writing about, where he said, could this be a spot deficiency in phosphorus? Now, let me give you some background information about this location. This location, I've been doing soil testing there for more than a decade. And the soil test levels were initially well over 100 parts per million on the Malick 3 test, which is an ample amount of phosphorus. That was a decade ago. And so I recommended don't apply phosphorus. You don't need to apply any phosphorus for this year. And the reason for that is because there's so much in the soil that adding any phosphorus would be completely gratuitous. And So the golf course superintendent there did not apply phosphorus year after year according to my recommendation. So the phosphorus goes down, down, down on the soil test. And at this time, at the time that picture was taken, the soil test phosphorus was somewhere around 60, 70 parts per million. So I wrote back after I saw those photos. I wrote back and I said, the guess that it might be phosphorus deficiency is a good idea. I recommend collection of samples to a 5 centimeter depth, that's 2 inches below the surface, and to a 10 centimeter depth, that is 4 inches below the soil surface, and from good and bad areas. By doing the soil test, we can at least eliminate phosphorus as the cause or identify it as a potential cause of those areas that were a little bit off color and that look like dry spots. And the idea with this is to check right at the surface of the root zone, the 0 to 5 centimeter depth or 0 to 2 inches, and also to check a little bit deeper in the root zone because typically we would be doing these soil tests to a 4-inch depth, 0 to 10 centimeters. And what I thought, and I thought this superintendent had a really good idea because basically he'd gone a decade without applying phosphorus. And if you think about it, there's a lot more roots near the surface. There's a lot more grass roots near the surface. The grass takes up more water right near the surface. The grass takes up more nutrients right near the surface. And I thought, could it be that we've been testing to a 10 centimeter depth? And it could be that deep in the soil, down at 3 or 4 inches below the surface, there's a lot of phosphorus, but not so many roots. And could it be that over a decade-long period of not applying phosphorus, could the phosphorus have been depleted right near the soil surface? Many of you will be familiar with the 40, 30, 20, 10 rule, which says that you can expect 40% of the water and nutrient uptake to happen in the top 25% of the root zone by depth, the top quartile of the root zone depth. And you can then expect 30% of the water and nutrient uptake to occur from that next quartile, from the 25th to 50th percentile in depth. So in the top half of the root zone, we'd expect 70% of the water uptake and the nutrient uptake to occur. And you go down to the next quartile, and that the third quartile, you would expect to have 20% of the uptake, and then the very bottom quartile, you would expect to have 10%. So that adds up to 100. That's not tested in turfgrass that I'm aware of, but I expect it is something like that, and that is something that I read about in a salinity paper as a way to predict where salts will be deposited and how you can manage root zones for salinity management. But it's also useful to consider where the nutrients are coming from, where the water is coming from, where the water will be depleted from in the soil as the grass is using water. So you can see, you can visualize, you can imagine that if you have 40%, almost half of the uptake is happening right from the top 25% of the root zone, and a full 70% of the uptake of phosphorus would be occurring probably from the top half of the root zone. You could see that the top of the root zone could become depleted in phosphorus more rapidly than the bottom of the root zone. So I thought, maybe, because we've been vigilant about avoiding phosphorus because the soil test results are so high. But remember, we're testing a full 4 inches or 10 centimeter depth. So I thought he may be onto something. So that's why I recommended to test it. And he did do the testing. The next part of the blog post says, soil samples were collected immediately. There were a total of 12 samples sent to the lab from 3 greens at the course with the possible phosphorus deficiency symptoms. Subsamples were collected from the bad areas and from the good areas. The bad areas are what in that photo are the slightly yellow areas, the areas that look a little bit dry. And then the good areas are the areas where the turf was the greenest. Each of the 3 greens tested then had 1 sample from the good turf and 1 from the bad turf. And furthermore, the samples were divided by depth. They were divided into 0 to 5 and 5 to 10 centimeter depths. That is, they were divided into 0 to 2 inches, the top of the root zone, and 2 to 4 inches, the bottom of the root zone, to check the phosphorus gradient in the soil. When the test results came back from Brookside Labs, where actually I happened to visit Brookside Labs today, that is a tremendous field trip. I think that was my 4th visit to the lab. I've already tentatively scheduled a return visit for another research project. I just love going to Brookside Labs and seeing a high quality agricultural, environmental, geotechnical laboratory that can test soils, can test putting green root zone mixes, can test organic matter, irrigation water, plant tissue, manure, fertilizer, lime, so many things. And to talk with the laboratory staff about some of the methods and some of the intricacies of the way the soil testing and laboratory analysis processes work, I just find that fascinating. Anyway, when the test results came back from Brookside Labs, where each of the 12 samples got a complete soil nutrient analysis that included both a Mehlich 3 test for phosphorus and a Bray 2 test for phosphorus, I checked the results. And the Bray 2 test results for P were similar to what was measured by Mehlich 3. So in the blog post, I just showed the Mehlich 3 test results. And reading from this blog post, I wrote, so were those weak areas on the greens phosphorus deficiency symptoms? Based on the test results, that is highly unlikely. And the reason why I say that is highly unlikely is in the good areas, in the top 5 centimeters or top 2 inches of the root zone, the average phosphorus in those good areas was 36 parts per million. That's by the Mehlich 3 extractant. Keep in mind that the MLSN minimum for phosphorus is 21 parts per million for the Mehlich 3 extractant. So we're above the MLSN minimum. There is some expectation that when we are above the MLSN minimum, there should be plenty of phosphorus to support good turf. And remember, from the good areas, the average was 36 parts per million. Now, here's the paradox, okay? From the bad areas, the average was 43 parts per million. It's 7 parts per million higher. There's 7 parts per million more phosphorus in the top of the root zone under the bad turf. The good turf actually is growing in soil that has less phosphorus. These were paired tests with 1 good sample and 1 bad sample per green. The difference between the good and bad areas on 1 green was negative 8 parts per million. That means the good area had 8 parts per million less phosphorus than did the bad area. On another green, the difference was also minus 8. And on another green, the difference was minus 4. So on all 3 of those greens, the difference was negative. The good turf was growing in soil that had less phosphorus near the surface than did the bad turf. Now, this is where it's interesting sometimes to check whether that's just a random occurrence or whether that could be what we would call statistically significant. So if we want to say how probable it is that this is a real difference and talk about this with some idea of how likely it is that this is a real difference and not just something that happened due to random variation in soil test phosphorus or random variation in the test results. To do that, we can do a statistical analysis. In this case, I did what is called a Bayesian analysis, and I prefer doing that because we can refer directly to the probabilities from the posterior distributions, and after we've done that analysis. If you want a little bit more about this, Henry Q and I talked about this in a recent ATC Double Cup podcast. And he explained quite well and quite clearly what a posterior distribution is and how the Bayesian analysis and Bayesian updating of our prior expectations, and then we add the data that we collect, we add our observations of the real world, we add the data of what we actually measure, and that updates our prior information, and it generates the posterior distribution, which we can then calculate probabilities from. And if you're interested in this, and I think, why not? Why not be interested in it? It is kind of fascinating, and it's used not just in turfgrass, but it's used in many this type of logic, this type of calculation, this type of statistical analysis is used in many fields, many industries. And so if you're interested in that, check out the recent podcast with Henry Q. Anyway, with those test results, so I'm describing here now what I did. I had a prior assumption. Actually, I would have expected before doing this that the good areas would have had a little bit more P. I think it's just natural that we would have the expectation that good turf is growing in soils that would have more nutrients in them. Good turf would be growing in soils that would be a little bit more full of food for the plants. That makes sense. So I had a prior assumption that the good areas would have more P at the top of the root zone and that the bad areas would have less. And I expressed that as a prior distribution. In this case, it's a normal distribution with a mean of 5 and a standard deviation of 8. I wasn't sure what the difference would be, but I didn't really think it would be 0. And I expected it probably was greater than 0. And in this chart, I show the prior distribution, which is most of the mass of that density curve is to the right of 0. It's positive. And then I show the posterior distribution, which is what happens after we add in those data that we collected, where one green was 8 parts per million less in the good turf. A second green was also 8 parts per million less in the good turf. And a third green was 4 parts per million less in the good turf. So when we add in those data and then we get this posterior distribution, we can say that given the test results that were actually measured, the posterior distribution has 98% of the values less than 0. So that means there's a 98% probability that the soil phosphorus under the good turf areas was actually lower than the soil phosphorus under the bad areas. Now, why would that be? Well, I explained in the blog post. I said, when you think about it, it makes sense that this would be the case. The greens had not been fertilized with P for more than 5 years. The clippings were harvested from the greens after mowing. Where the grass was healthier and producing more leaves, there would be more phosphorus removed from the soil. Over time, phosphorus was depleted at the top of the root zone. That really makes sense, doesn't it? Because if the grass is growing more and you don't apply phosphorus, then the grass is going to use phosphorus from the soil, and the grass that grows more is going to deplete the soil phosphorus more rapidly. That makes sense. And when we think about it that way, it's very understandable why the good turf would end up over time. I don't think this would happen in 1 week or 2 weeks or 3 weeks. You probably would not get a statistically significant difference in that short amount of time. But in this case, over a multi-year period, it turns to be a substantial and statistically significant difference where the good turf It's growing in soils with lower nutrient levels. And then I hope somebody listening will have some data that will support this, or perhaps you'll have some data that will contradict this. I felt like I had a number of other examples, and it took me a long time to get around to writing this post because I had the idea of that's really interesting, and I had in the back of my mind the idea that I'd seen data like that before. And I thought I probably have a number of examples if I can just remember which ones they are, and I can share example after example that would say this is not always the case, but it is also not an uncommon case. In fact, it's probably more common than you expect to find that good turf will deplete the soil nutrients, and consequently, over time, you find that the good turf is growing in soils. When clippings are harvested, the good turf will be growing in soils that has lower nutrient content than the turf of a poorer quality. That was the idea. But then I couldn't remember any of those perfect examples from before. But then I checked some data that I collected recently in Thailand, and this was soil test phosphorus on 30 different putting greens in Thailand. And I put a picture of all of those in the blog post. And I asked the question, I said, the example above was for one golf course. And I asked the question, would this paradox extend to other situations as well? Let's see, when was this? Late 2021 and early 2022. Brad Revel and I, Brad from BRT Agronomy in Thailand, we divided up the responsibilities, and he sampled. We met and did the first golf course together. We did greens at the first couple of golf courses together to make sure that we were doing the same procedure. And then I took my sampling tools and collected at some golf courses at some putting greens around the central Thailand area. Then I left all the tools with Brad, and he went around and collected at some other greens in the central Thailand area. So over a couple month period, we collected from 30 greens, and these greens included Bermuda grass, seashore paspalum, and zoysia putting greens. And we rated the greens on a 5-point scale, and the greens were rated as they were rated on a 5-point scale that I quite like, where the highest scale, the highest rating you can give the grass is, I can't imagine how it could be better. The next the next level is the grass could be better. But I mean, it's very good, but it's not like it's not like at the level where you can't imagine how it could be better. The third level is acceptable conditions, which is something like the NTEP 6 rating or the NTEP 5 rating, which is minimally acceptable conditions. And then we get down to the two levels that are less than acceptable, where I rate them as easy to see how it could be made better. And the worst rating that I give it is poor or terrible. Sorry, I'm reading off the blog post and messing up with my scale. I'm trying to remember my scale in my head. And I'm gonna correct this, okay? Let me bring up, let me see. I'm gonna find my rating scale and make sure that I get it right. Okay. Here we go, okay? Here's the 5-point scale that I use. And I'm not going to confuse myself this time. The top level is can't imagine how it could be improved. The next level, almost perfect with a few minor blemishes. Then the middle level is acceptable conditions. And the next one is easy to see how it could be made better. And the worst rating that it can receive is awful conditions. So that maps to a B, C, D, F scale. And if we multiply it by 2, we can quickly get it onto a NTEP 1 to 9 scale. So I find that this is a easy way to classify grass, because I can classify it as can't imagine how it could be improved, almost perfect with a few minor blemishes, acceptable conditions, easy to see how it could be made better, and awful conditions. So that's the type of mapping scale that I like to use. So let's see. Anyway, so how did I analyze the data here? Well, these greens were all rated. These 30 greens that we sampled from, we took soil samples from them and we rated them on a 5-point scale. So anything that was acceptable conditions and higher, or C or higher, the C score or higher, those are classified as good. And any greens at the 2 bottom levels, D or F, which are easy to see how it could be made better, or awful conditions, those are classified as poor. So we separate into good and poor by dividing based on that 5-point classification, and we divide that then into 2. And I had a prior assumption that the Mehlich 3 phosphorus would be about 60 parts per million. That is a reasonable expectation considering that the median Mehlich 3 phosphorus in the Global Soil Survey was 68 parts per million. And then I check the results, and across those 30 greens and across those greens that each got tested for Mehlich 3 phosphorus, and each of those greens that was rated and then classified into good or poor categories, the average Mehlich 3 phosphorus for the good greens was 30 parts per million. The average Mehlich 3 phosphorus for the greens that was rated poor, the greens that were rated poor, was 43 parts per million, a 13 part per million difference. And in the chart that I show, the prior distribution assumes that all of those greens would have a median value for phosphorus of 60 parts per million, which is quite similar to what we would expect for putting greens. But in fact, the good greens were at a median of 30, and the poor greens were at a average value of 43. So those are the results. So once again, the soil phosphorus was lower under the good turf and higher under the poor turf. And if we just subtract, if we take the difference between those posterior distributions, then we get the posterior distribution of the differences between good and poor green Mehlich 3 phosphorus. And in this case, there's an 87% chance that the average phosphorus from good greens in that data set is actually lower than the average phosphorus from the poor greens. So we had 98% in the one experiment on a single golf course, and then in this survey, 87% of the probability suggests that the good performing turf is growing in greens that on average have a phosphorus level lower than the bad turf. That may or may not surprise you, but I think you'll understand why that could be, because if you tend to put relatively low levels of phosphorus over time, then grass that grows better, grass that's healthy for other reasons that are not related to the phosphorus, reasons such as better irrigation coverage, perhaps better drainage or better light, or other reasons that I am not thinking of right now, that I'm not aware of. Whatever it is that makes the grass grow better and more clippings get removed from that grass, over time that's going to mine or deplete more phosphorus from the soil. So that's really interesting. I think it's a nice paradox, and this is a fun thing to be aware of. Now, here we come to the part of like practically, what should we do about this? And so I put a section in this blog post that has the heading, what to do about this. And I answered it with one word, which is nothing. And I said, just be aware of this phenomenon. If you weren't aware of this before, knowing that it happens can help you put your soil test results and fertilizer recommendations into context. And I also recommended using MLSN, and I also suggested, or the final two sentences, or the final paragraph says this: with this approach, one can apply reasonable amounts of fertilizer, ensuring the grass is supplied with all of the nutrients it can use. There's no paradox in that. So that is the blog post. And I have a few other comments, I think, to summarize this and to give it even a little bit more context and explain why being aware of that is enough, and you can just do nothing about it, at least if you're using MLSN. Because the notes that I made are that we often find better turf in the worst soil. And remember, this is not a farming competition. It's not something where we're trying to have the absolute healthiest turf. And people sometimes talk about turf health, and I've probably used that terminology myself, but I try now not to use it too much, because we don't really want the healthiest grass. We want the grass that is healthy enough to support the desired playing surface. If we were really trying to have the healthiest grass, we wouldn't mow it at 2.9 millimeters or something like that. We wouldn't apply the nitrogen rate as low as we do. We would grow more grass and grow a larger root system. So if you think about that, we're not necessarily trying to grow the healthiest grass. So it does make sense that maybe sometimes it would be good to have nutrient levels that are in moderation. We don't want to grow in pure compost. You know, if you want to talk about a healthy soil, it's going to be a soil that might have so many nutrients in it that the grass grows too fast. It grows so much that you can't really keep up with mowing. And although that might be considered a healthy soil and that might be considered healthy grass, if you look at the type of turf grass that's produced, that tends not to be the type of turf grass surface that we would really want to have. And then when you think about what to do with it, I think it makes sense to go back to thinking about fundamentally what we're trying to do with fertilizer supply to turfgrass or nutrient supply to turfgrass. And I think we can start by just ignoring the soil entirely and just think about how much of each nutrient the grass will use. So we can think about supplying 100% of the nitrogen that the grass can use. We should think about supplying 100% of the phosphorus the grass can use, 100% of the potassium the grass can use, and so on. And it's very easy to figure out how much that is, because the amount of nitrogen that is supplied puts an upper limit on how much the grass can grow. So once you know how much nitrogen you apply, then you can figure out how much potassium the grass could possibly use, how much phosphorus the grass could possibly use, and so on. There's a lot of information about that at Pace Turf. There's a lot of information about that at the ATC website. I recommend you, if you're a Pace Turf member. If you're not a Pace Turf member, I should say, what are you waiting for? Because I write about this type of stuff and provide this type of practical information so that you can know how to calculate this. And you don't really even have to calculate it, because the math is so simple, and you can just kind of figure out in your head, if you apply this much nitrogen, the grass needs this much phosphorus, needs this much potassium. I've not mentioned the soil at all. I've just been talking about how much the grass is using. And then we can consider that we just need to make sure that the grass is supplied with that. So we start with that default amount of expected nutrient supply, and we can just skip soil testing altogether. I think we can be a lot more efficient if we do soil testing, if we interpret the test results in the right way. But we could start by just applying that many nutrients, and where soil testing comes in, you take a soil test and then you find out how many nutrients are in the soil. And if you interpret them using MLSN, which is a very efficient way to do it, then we get a site-specific adjustment for your grass and for your climate and for your site and for how many nutrients are in your soil and for how rapidly you intend to grow the grass. We can then make an adjustment for accounting for whether the soil will be able to supply all that the grass uses, or if we need to supply some or all of that element as fertilizer. So basically, I want to summarize this and kind of wrap it all up by saying the reason why I say that you can do nothing about it is because if you're not soil testing, then the only logical way to me for professionally managed turf to manage would be to be supplying 100% of plant use. So if you're doing that, you're never going to have a deficiency. And the way that I recommend doing it is using soil testing and interpreting it properly. For me, that involves using the MLSN approach. And if you do that, you're also going to make sure that no matter whether you have good turf or whether you have bad turf, and whether you've got that paradox going on where the bad turf is growing in soils that have higher nutrient levels or good turf is growing in soils that have lower nutrient levels, no matter whether you have that type of gradient going on that kind of seems like a paradox, or whether you have the situation that you might expect where the bad turf is growing in soils that have lower nutrient levels and the good turf is growing in soils with higher nutrient levels. No matter what situation you have, if you use the MLSN approach and interpret the results that way and develop a fertilizer recommendation that way, you will also ensure that you prevent nutrient deficiencies and you'll make sure that the grass is supplied with all the nutrients that it can use. And I made a note here also. I said the good turf is more likely to have a nutrient shortage than low quality turf. And this is what I'm going to close with, is just to point out that if you extend these results and you think about what another implication of this is, that putting green that I showed you from my soil testing client from October of 2022, the good turf had lower nutrient levels in the soil. The good turf was growing more and producing more leaves. And that's going to decrease the soil phosphorus even more. And you can see that if we project that timeline into the future, you'll see that the good turf would be more likely to be growing in soils that don't have enough phosphorus. And that is perhaps not intuitive, but that is the reality of the situation, which is why it makes sense to be aware of that. It makes sense to do soil testing carefully. I recommend doing most of your soil samples to a 4-inch or 10 centimeter depth. If you're one of ATC's soil testing clients, you've been getting specific instructions about what I recommend regarding sampling depth. And I recommend taking 20% of the samples with the sample split to a 0 to 5 centimeter or a 5 to 10 centimeter depth. So we look at the gradient, we look at the nutrient and pH and all of that right at the surface. And then we look in the bottom half of the root zone and find out what that is also. So most of the samples are to the full 10 centimeter depth, and 20% of the samples I recommend splitting by depth so we can look at this in detail. And then if you interpret using MLSN, you'll certainly get a recommendation that is going to supply all the nutrients that the grass can use. So this is something that I'm so glad to share with everyone, and I'll be interested to hear if anybody has some feedback about that phenomenon. If you have ever seen this yourself, or if you have seen the opposite. Because in some cases, especially in areas that are heavily fertilized, you may find the opposite. But in areas that are lightly fertilized, you'll be able to detect this because the good performing turf is depleting the nutrients from the soil because it grows more. That's pretty cool. All right. Thanks everyone for listening and for watching. I've been on a bit of a hiatus from the show. I've been quite busy. I took a trip to Japan, and that included a number of flights, and I took two trips to the island of Kyushu within a week, and I was also in Shizuoka, right at the base of Mount Fuji, and I was in Tokyo. I was all around in Japan, and then I flew to the U.S., and in a short time span, I've visited 12 golf courses in 7 states so far. I've still got a couple more states and a couple more golf courses that are yet to be visited. I have happened to visit 3 universities in 3 different states, meeting with professors and attending the Rutgers Field Day. And I also met a professor from from Ori Georgetown Technical College. I met Jim Huntoon, or maybe he's a associate professor from Ori Georgetown, and we visited a golf course under construction together. So kind of 4 university connections there. That's been good too. So I've learned and observed from golf courses that I've visited. And I think I'll do some more blog posts, maybe share a few videos or photos and some of the things that I've learned, from the university visits and the things that I have learned from the golf course visits. So for me, it's just a matter of time. I have no shortage of ideas, and I hope to have some more time soon to share some of that information. Anyway, that really will be the end of this episode, and I'll sign off now from a hotel room in the Chicago metropolitan area of the United States of America. I am Micah Woods. Bye-bye.